Okay, 4.3 is multiplication rules. And we kind of talked about it a little bit in 4.1 without actually talking about it. When we went through and made those tree diagrams and tried to figure out how many possibilities there were and made the sample spaces, I didn't tell you specifically that there's a way to figure out how many there are without making them all, and that's what we're doing today. So, the first thing is that two events, A and B, are independent if what happens in A doesn't affect what happens in B. Okay? These are different than mutually exclusive. Independent events, whatever happens in the first event does not affect the second event. When you have independent events, to find out the probability of both of those events occurring, this is the first multiplication rule. So if these events are A and B, the probability of both A and B happening equals the probability of A times the probability of B. So here's a little example. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. Now, these events are independent because what happens when you flip the coin does not affect what happens when you roll the die. One doesn't affect the other. One doesn't impact the other. They're totally kind of separate, which makes them independent. So go ahead and find the probability based off of that happening. What is the probability of getting a head on the coin? 1/2, right? 1 out of 2. What's the probability of getting a 4 on a die? 1/6, because there's one way to get it. Okay? So what you should have had, 1/2 times 1/6. How many had that? Good. So what's that equal? 1/12. Multiply across the top, multiply across the bottom. Okay? How many had that? Okay. Let's look at another example. This is on page 212 in your book if you want to screenshot it from your book instead of taking a picture of the screen. And I'll talk through some important parts here. The key to this problem is that after a ball is selected, it is replaced. Meaning, every time a ball is taken out of the urn, there's the same number of balls to begin with. So each event is independent because you start with the same number of balls in the urn every time. If it wasn't, if we didn't put the ball back in after we pulled it out, then they wouldn't be independent anymore. Those would be dependent events, and we're going to talk about that next. So again, every time a ball is pulled out, the same number of balls are in the urn at the beginning of each event. So go ahead and try to come up with the probabilities for these three scenarios, and then we'll come back and see what we can figure out. See if you did them right. Again, each time a ball is taken out, that counts as one event. The second time a ball is taken out, that's the second event. So in terms of your setup, this is kind of how you want to think about it. In the first scenario, the first event's drawing a blue, the second event is drawing a blue. That's how you get the two blue balls. Okay. In B, the first event's a blue, the second event's a white. In C, the first event's a red, the second event's a blue. So that's the setup. So hopefully that's what you've been doing. And then we'll take a look and see what you got. What's the probability of pulling a blue ball out of the urn? 2 out of 10. There's 2 blue balls. There's 10 balls total there. So there's 2 out of 10 chances that you will pull a blue ball out. Okay. So if that, and then if you put it back in, the probability of drawing a blue ball again is the same thing. So in the first one, you're looking at a probability of blue times the probability of blue, 2/10 times 2/10. Okay. Which is 1 over 125, or 1 over 25, excuse me. How many had that? Okay, good. So the probability, we know the probability of blue. What's the probability of getting a white one? 5 out of 10, or 1/2. So for the next one, again, it's probability of blue times the probability of a white. So that's going to be 1/10. How many had that? Good. And then a red, what's the probability of getting a red? 3 out of 10. Okay. Blue is still 2 out of 10. That's going to give me 3 out of 50. All right. Any questions on independent events, finding the probability of independent events? Okay, good. Let's talk about dependent events. And there's notation stuff here. We'll get to that in a second. When the outcome or occurrence of the first event affects the outcome or occurrence of the second. So now, what we're saying is what happens in the first event impacts the second event. We can't really think about the second event until the first event is completed, because what happens there is going to impact what happens in the second event. Those are called dependent events, and the probability is going to look a little bit different. One of the things that's going to happen with dependent event types of problems is you're really going to want to read the question carefully and make sure you have a good understanding of what's happening. That's going to really impact your ability to do these problems well. A good understanding of what's happening in the problem is really going to be important. So here's an example of a problem where the events are dependent. Okay. What's the probability of drawing a king from a deck of cards and then drawing a queen? The key part here is that we are not replacing the first card. So our sample space on the second event will actually change based on what happens in the first event. In other words, it's not going to be 52 cards every time. The second event, we've taken a card out of the deck. So that will impact how many cards are left to choose from, which is why this is a dependent event instead of independent. Now, before we solve this problem, I want to do the multiplication rule 2 for two events that are dependent. Okay, the notation looks a little different now. Instead of it just being the probability of A times the probability of B, we have this conditional probability over here. Okay, and what this means over here is the probability of B occurring given that A has already occurred. That's what that notation means. A's already happened. Now find the probability of B, knowing that A has happened and impacts the probability of B. So that's what that notation means. And then we'll get on and solve it. Because solving this problem is not that tough. Right? I think we should be able to do it fairly easily. And we'll do that. I'll do that on the next screen. Or actually, you guys can go ahead and do it. Shouldn't be too bad. Go ahead and figure that out, and let's see if you did it right. All right. Did you guys figure out the answer yet? All right. Try and figure out the answer for the question about the kings and queens. Yeah, don't get hung up on this whole thing. All this means is finding the probability of B, knowing that A has happened and it impacts it. It's not a slash. It's not a division. It's not multiply. It's just a notation letting you know that these are not independent. These are dependent events. That what happened in A affects B. That's all it means. Okay. So what you've got to do now, the probability of A, you've got to find that. So in this case, the probability of A is drawing a king. The probability B is drawing a queen, but what happened in that first event is going to impact the probability of the second event. That's all it's saying. Okay? So in the first event, how many ways can you draw a king? 4 kings out of how many probability? 4 out of 52. Okay. Now, how many cards were drawn out the first time? 1. So the probability, while the probability is 4 out of 52, we only took 1 card out of the deck. Which means how many cards are left? There are 51 cards left. What is the probability of drawing a queen? How many ways can you get a queen now? 4 out of 51. Okay? This is what your setup should be. So even though there's 4 ways to draw a king out, we still only draw 1 card in this event, which means I'm down to 51 cards afterwards, and there's 4 queens. So it's just a matter of simplifying this now. Okay? Are there questions before we come up with the answer? Yes?
Can you explain how you got 51 again?
Because we drew 1 card out in the first time. So that means instead of having 52 cards in the deck, there's now 51 cards. Yep. Okay. Again, the probability of drawing a king. Now, if we went through and actually did this, 4 out of 52, that's 1 out of 13. Our probability is pretty low on pulling a king out the first time. Okay. Regardless, that's what the probability of doing it is. And once you pull that card out, we don't put it back in. That's without replacement. Okay. So now we sort of set it aside. And now we have a deck of 51 cards because 1 card's gone. There's still, the chances are of getting a queen, there's still 4 ways to get a queen, and so that's why it looks like that. I simplify that, you get 4 out of 663. Okay. So, the chances of drawing a king and then a queen, if any of you have ever watched poker or played poker, okay, it's very low. 4 out of 663 is not those aren't good, that's not a good probability. The likelihood of that happening, a king, then a queen, is not very high. Okay? Let's look at another example. Okay, let's talk about, again, jacks, or 3 cards. 3 cards drawn from an ordinary deck, not replaced. So the probability of getting 3 jacks in a row. Okay? Again, think about this if you've ever watched poker. I mean, 3 of a kind is kind of a good hand. It's not a great hand. It's a pretty good hand. So the likelihood that you would get 3 jacks right off the bat. Go ahead and do this one. Let's talk about that. How many events are there here? There's 3, okay? So if you want to think about it that way, this is the probability of getting a jack, and a jack, and a jack. And because the cards are not replaced, man, that is just terrible looking. Let's fix that. They are dependent events. They do not affect. They do affect each draw. Now, so for the first one, all right. What's the probability of drawing a jack on the first draw? 4 out of 52. Okay, so we've pulled a jack out and we set it aside. Okay, what's the probability of drawing a jack again? 3 out of 51. See, now there's only 3 jacks left in the deck.
You're saying if I get a jack every time?
Yep.
Okay.
So what's the probability of getting a jack on the last one? 2 out of 50. So see how each draw impacts the next one. Okay? So 4 out of 52 times 3 out of 51 times 2 out of 50. Simplify that. That's even smaller. 1 out of 5,525. So the likelihood of 3 jacks is pretty low. So card games, they're all based on probability. Okay? The reason that 4 of a kind has higher value than a pair is because the likelihood of getting 4 of a kind is much smaller than getting a pair. Alright, let's talk about one more thing. Let's say all I wanted to do was find the conditional probability. Okay? Let's say all I wanted to do was find the probability of getting the 3rd jack. not the probability of 3 jacks in a row. Okay? So, this is the same multiplication rule. You don't need to write it down again. I'm just putting it up here to show you. What we're trying to do now is I'm going to show you how to find the probability of just the conditional part. Okay? So in other words, I'm going to get that conditional part by itself. And the way I do that is to divide both sides by the probability of A. And that will get my conditional part by itself. And this is where the conditional probability rule comes from. Okay? Don't take a picture yet. It's going to get better. So here's the conditional probability rule. Okay? This, the probability of B happening, knowing that A's already happened, is the probability of A and B divided by the probability of A. Okay, so we can isolate that one just to figure that out. And these are the problems that are going to get really wordy, and you're going to want to really take your time with to make sure you understand what's happening in the situation. Okay. So here's the problem. Please take a picture of that. Don't write it down. Too wordy and too long. But this is what I'm saying. These problems will get wordy. So, here's what's happening. There's a box. It's got black and white chips in it. A person's going to pull 2 chips out without replacement, meaning they're going to pull one and then pull another one. They're not putting that first one back in. Probability of selecting a black and white. So, in other words, doing that whole thing. Pull a black one, then a white one. That probability is 15 out of 56. The probability of pulling a black chip on the first draw is 3 out of 8. So we're trying to find the second probability. We're trying to find the probability of selecting the white chip on the second die, knowing that we pulled a black chip on the first one. So we're just trying to find the second part, that conditional probability. Okay. So here's what we're really trying to find. We're trying to find the probability of pulling a white, knowing that a black has already been pulled. Okay, in this case, I'm going to do B equals the event of selecting a black chip. W is the event of selecting a white chip. Okay, so why don't you go ahead and try to use that formula to find out what the probability of pulling the white, knowing that a black's already been pulled, is. So that formula that we had on the previous screen, that's the one you want to use. So give that a shot. Okay, so the formula says that's just going to be the probability of a black and white divided by the probability of a black. Okay, that's what the formula says. These are dependent events, just working on finding the second event. So what's the probability of a black and a white? 15 out of 56. What's the probability of black? 3/8. Now, one thing to consider, especially when we start working with fractions like this, is that really means, this problem here, this giant fraction means the probability of a black and white divided by the probability of a black. The reason I'm doing this is because this is where you're going to have to remember your fraction rules, right? So just like we said, it's going to be 15 over 56 divided by 3/8. Well, this is a keep change flip for those of you who don't remember. Okay, most of you will probably run to your calculator and punch it in. Okay. What is it? Ashton? 5 over 7. Okay, so the probability of drawing a white chip, knowing a black's already been drawn, is 5/7. Yeah. Well, at the same day, it's the same. You're doing the same thing. 3/8 x equals 15 over 56. You're going to have to divide by 3/8, right? Or times both sides by 8/3. It's the same thing. Okay, so I'm just doing it in one step. All right. Now, this example is sort of a base level example. You're going to do some problems tonight that have decimals in them, that have percent probabilities in them. Use the formulas the same way. All the problems we worked on today had fractions. Don't get freaked out when you start seeing decimals and percent probabilities. It works the same way. Okay? Alright, that is 4-3.